Now let's make a case of a general form of separable differential equations. So by that I mean that I am trying to write a general equation that can represent any equation that we might come across, that is that we are able to apply the technique of separation of variables to. So in general, if we write an equation in this form, function of x times a function of y, this equation demonstrates a general form of separable equations. Why? Because there is a function of x, this function only depends on x, and this function only depends on y. So easily we can transform this equation into dy divided by g of y is equal to f of x times dx. Now we can see that we have brought g of y over to this side, and as I have said earlier, we have implicitly made the assumption that g of y is not equal to 0. This is an assumption that we have implicitly made. So to compensate for this assumption, we have to find the lost solutions that we are losing in making this assumption manually, and then add the solutions to the overall set that the general solution gives us. That way we will have all the solutions of the differential equation that we are trying to solve. Now as we are assuming that g of y is not equal to 0, the cases where g of y will be equal to 0, these are the cases for which we are losing the solutions. So if we simply set g of y equal to 0 and then solve this equation to find the roots of g of y, then those roots, let's say y comes out to be y is equal c over 31. This is the root, let's say. Then this is a solution that will get lost when we are trying to apply the separation of variables technique. But as we have already found this solution using our concept, that then now if we add this solution to our set of solutions that the general solution gave us, then we will have all the solutions. This solution will not be lost. Even though it was lost in the process, we have found it in some other way. So the concept is that we have to find all the roots of the function of x that is on the right hand side. That way we will be able to find all the lost solutions that we will lose when we are trying to apply separation of variables. So let's take a look at another example. Let's say we are asked to find all the lost solutions. So all the lost solutions of this equation. Y prime is equal to x plus 1 times e to the power x times y squared minus 8y plus 7. So here what we are trying to do is we are trying to take this part. This is g of y for us. So what we eventually plan to do is bring this part over to this side and write dy over y squared minus 8y plus 7, and we will get a dx here, and we will take it to the other side, and we want to write x plus 1 times e to the power x dx. This is what we are trying to do. So as we are bringing this side over to the left side, So this is our g of y, and the roots of this part will give us the lost solutions. So let's take a look at how we can go about finding the roots of this expression. Y squared minus 8y plus 7 is equal to 0. If we do a middle term break, then we will find y minus 7 times y minus 1 is equal to 0. And from here we can say that y is either equal to 7 or y is equal to 1. And these two are the lost solutions. These two solutions will be lost when we try to solve this equation using separation of variables technique. So these are the lost solutions. Now you will remember that we talked about an equation and claimed that it was the most important differential equation we will encounter in our course. Do you remember what that equation was? Even if you don't, I'm going to write it for you here. So that equation was y dot is equal to a constant times y. This was the equation that we claimed to be the most important differential equation of this course. Now that we have learned a way to solve very simple differential equations, let's see if we can apply that way to solve our most important differential equation. As it turns out, our most important differential equation is actually a very simple equation, and we can solve it using separation of variables. So first we will do dy over y is equal to k dx, and from there we will integrate and get natural logarithm of absolute value of y is equal to k times x plus c. Let's say this is c1 because we will get another variable later. Now if we make it like modulus of y is equal to e to the power kx plus c1, and later y would be equal to plus minus e to the power c1 times e to the power kx, and from there we will consider all of this to be a single constant capital C, and write our solution as capital C times e to the power kx. Now, as we have previously discussed, this is the solution that we claimed at first and then proved that this is the solution. Now we have applied our newly gained knowledge and solved it for ourselves to get at this solution. Now the issue here is that some of you must already have noticed. It seems as if there was no lost solution in this equation, because the term g of y here is equal to y. This is the g of y. Now if we want to find the roots of g of y here, the only root would be y equal to 0. So this should have been the lost solution. But as it appears that if we simply set c equal to 0, as this is now a parameter, if we set c equal to 0, it gives rise to y equal to 0. So it appears to be as though we haven't lost a solution here. Now, is it a conceptual mistake of ours that we are thinking that we haven't lost any solution? Or is it truly so that this is an exceptional case where we are not losing any solution? Let's take a more in-depth look. If we do a bit of backtracking, we will see that c is actually equal to plus or minus e to the power c1. c the parameter c, this is not the original parameter. The original parameter is this. This is the original parameter. Let's say original parameter. And this is the one we took for simplicity. Simplicity. This is the one that we took for simplicity. Now, to set this parameter to 0, we must first be able to set this whole thing to 0. Now let's see in which case all of this would somehow be equal to 0. The only way this will be equal to 0 is if we set c1 to negative infinity. That is the only way this will be 0. Now, as I have mentioned again and again during the last lecture and also in this lecture, that setting something to negative infinity is practically impossible. Think of the largest number that you can think of in your head. Is it even close to infinity? No, it's not. Infinity is billions of billions of billions times larger than what the largest number that you can think of. So we can actually never get to infinity to set it as infinity and get this one to be 0. What we have implicitly done is we think that this is the original parameter. Now if we simply set this to 0, this becomes 0. But that is not the case. We cannot control this. We only can control this parameter. So we need some kind of value of this that makes all of this 0. But there is no value for this except negative infinity, which we are not considering in this case because it is impossible to get to. There is no value of this that can be set so that all of this can be made to be 0. So now, as we will use all of these equations to describe real life systems, for all practical purposes, this thing can never be 0. So it seems as if we set this to 0, we are not losing any loss solution. But in reality, we cannot set this to 0. So actually we do end up losing this solution. This is actually a loss solution. So it turns out that when we thought that we were not losing any solution, it was a conceptual mistake. It is not any exception. This is not a special case. We do end up losing the solution y equal to 0 in the regular way, and we have to find it in a manual way. Now let's take a look at some solutions that are said to be blowing up. I will explain what I mean in a minute, but first let's take a look at an example that will explain it better. So the equation that we are going to take a look at is y dot is equal to y squared, and we are given an initial condition y of 0 is equal to 1. So we are asked to solve this system and find a solution. So let's apply our technique that we have done. dy over y squared is equal to dx. So if we integrate this, we get negative 1 over y, and that will be equal to x, and there will be an integration constant. Now if we rearrange, then it comes up to be y is equal to negative 1 over x plus c1. Now let's use our initial condition here. we are told that y at x equal to 0 is 1. So we have to set x equal to 0 and y equal to 1. So let's say y equal to 1, and that will be equal to negative. It will be equal to x equals 0 plus c1. So c1 comes out to be minus 1. So our solution for this system is, we will just put the value of c1 in the general solution, and we will get y equal to 1 over 1 minus x, and this is the solution that we arrived to. Now let's take a look at how this behaves in a graph. To graph this, I will show you how to think of graphing this. Let's just take this part over to this side. That will help us in thinking. So if we write it like this, then we see that this and this, all of this makes it an equation that is of the similar type as xy equal to 1. A similar equation. Now, what do we remember about the graph of xy equal to 1? We remember that the graph of xy equal to 1 was something like this. Now, let's transform this graph to fit this equation. As you can see, there is a negative sign here. So the graph will look as its mirror. So let's make it its own mirror. So the graph will be this and this. Now we see that there is a x minus 1. There is not only x, it is x minus 1. So the graph will shift 1 unit to the right. So the final graph looks like this. If this is the line x equal to 1, the final graph will look like this. This is the graph that we are trying to get. Along this is x and along this is y. Now you can see that this graph is not a continuous graph. There is a break at line x equal to 1. This is the point. This is the point 1 equals 0 and 1 comma 0, and this line is x equal 1. So we can see that as x tends to 1, as x approaches 1 from the right side, let's say from the right side, I'm not using 1 plus or 1 minus, I'm just using right side and left side just to make you visualize it better. As x is approaching 1 from the right side, y is tending to negative infinity. As x approaches 1 from the left side, y approaches positive infinity. So there is no way for us to get away from this curve and go to this curve in a continuous manner. If we want to follow the graph of this equation from negative infinity to positive infinity, we cannot do it, because let's say we are coming from negative infinity, we come towards 1, and we can never get to 1 because this is asymptotic to 1. This gets slowly closer to 1, but until y reaches infinity, it does not touch the line 1, and so we can never get over the line 1 and go to this side. And it is also the case for this side. If we approach it from positive infinity, we get closer and closer to the line x equal to 1, but we can never get over it because this line does not touch the line x equal to 1 until y becomes negative infinity. So we can say that there is two parts of the solution. This is not a single solution because this is not continuous. We cannot say that this solution exists in only one interval because there is a break and it has split itself into two solutions. We can say that it has two solutions. So what are the two solutions? The two solutions look exactly the same, but the conditions of the solutions are different. So the first solution would look like y of x is equal to 1 over 1 minus x when x ranges from negative infinity to 1. It is not equal to 1, this is less than 1. And the second solution is y of x is equal to 1 over 1 minus x, and it ranges from 1 to x to infinity. These are the two solutions of this differential equation. They look the same, the expression is exactly the same, but the conditions of them are different because this expression is not true when x is exactly equal to 1. That is the reason we have had to split the solution in two ways. Now, which solution is ours? We cannot have both solutions because it is a direct case of initial value problem. And as we know from initial value problems, we have to pick out a single solution. We cannot take a range. Then, which solution would work for us as we cannot take both? Now we see that if the solution ranges from negative infinity to 1, it actually encompasses the point where we are given the initial condition at. We are given the initial condition at this point. This is the initial condition point. So we see that this is the line that contains our initial condition. So this solution must be the solution that we are looking for, because as we can never get over from this line to this line, and one of the points of this system is contained on this line, then all of the points of this system must be contained on this line, as no one can get over from this line to this. If someone is over here, all of them are over here. That's the argument. So this is the solution that we are looking for. This is not our solution. So from here what we understand is that if we really want to be meticulous about our solving differential equations, we have to mention the range of our solutions. If we simply write that the solution is y of x is equal to 1 over 1 minus x, then it is implicitly assumed that x varies from negative infinity up to positive infinity without any break. But this is not the case. Our case is that x does not include 1. So we must say that this is the solution and this is the range that we have, we can let x to vary between, and this is not